Well, thank you very much. Thank you for the great honor. Thank you for the introduction. Thanks to the Tylers for their vision in creating the prize, and to the committee that awarded it to me, and to all of you who have come here today to share this with me, and especially to Amber Brown for all the work she's done in putting this together. That's you, Amber. Thank you. The central problem facing societies, in my view, is how do we achieve a sustainable future? Can we grow economically without compromising options for future generations? This is basically the way the Brundtland Report defined the problem. How do we leave for future generations the same sort of opportunities we have? And for those of us who remember Pogo, we may remember his famous quote, "We are faced with insurmountable opportunities." And that's really what my focus is going to be today. It's on obstacles and opportunities in environmental management. The bigger the obstacle, the bigger the opportunity. So I've laid out, and as I thought about this, 5 things that I think are obstacles to doing a better job. The first I call the swamp of uniqueness. The notion that every ecosystem is different from one another. Indeed, every ecosystem is unique, but that doesn't mean that we can't derive generalities. We can still develop a functional taxonomy that allows generalizations. This is one of the few technical slides I'll have today, but it's very simple. It says here, if we map based on the average temperature and the average precipitation of a region, we can't predict exactly what species are going to be there, but we can predict where we're going to find tropical rainforest, where we're going to find temperate grassland, etc. So there are some generalizations, some generalities that we can derive that help us to develop a theory of the structure of ecosystems. Every management challenge is unique. The lobster gangs of Maine have worked out a system for managing the lobster fisheries. The water temples of Bali, this is a wonderful story that my colleague Steve Lansing has developed. Don't have time to talk to you about it, but it's a system that's self-organized where, based on the priests who help to mediate the water distribution systems, it's a system that's developed over many centuries. The government realized how inefficient this was and brought in a bunch of programmers, and everything collapsed. So they went back to the natural system. The Tribunal de las Aguas of Valencia, it's the oldest democratic institution in Europe, a millennium old, resolves irrigation disputes. So all of these share common features of a problem I'll talk a great deal about today, namely the problems of the commons, the problems of public goods, and common pool resources. Fishermen sharing grounds not only with each other, but with oil rigs in the background. How do we share these grounds? Dealing with these problems requires a systems level approach, and I took this off the NOAA website. We need to be thinking about marine ecosystems as ecosystems, with species interdependent on each other, no longer managing one species at a time, which has been the history. So these sorts of examples argue for the need for a theoretical and a conceptual framework based on these systems as complex adaptive systems. I'll tell you more about that. And adaptive environmental management, and I'll tell you a bit more about that. But we need theoretical approaches, and that's where the mathematics comes in. I'm not going to take you through these equations. This is really artwork. But meeting that challenge can benefit from a mathematical framework. And indeed, this is not new. This is a great mathematician, Vito Volterra, known among mathematicians for his work on integral equations and things of that sort, but attracted to problems of the fluctuations in the Adriatic fisheries. Careful, there's of the Adriatic fisheries nearly a century ago. And Volterra, working with his son-in-law, helped to work out mathematical models describing these fluctuations, which still infuse the teaching of theoretical ecology today. So that's the first obstacle. The second is what I call the temple of the discipline. In a university, we know that academia creates silos in which people work within their own disciplines and don't talk to each other, don't know how to talk to each other. And we really need to, for the problems I'm going to talk about today, to encourage true multidisciplinarity, not just between biology and mathematics and physics and chemistry, but to the social sciences and the humanities and business as well. So we need to find ways to develop dialogues. The third obstacle is the fact that ecosystems are complex systems. I'll talk a great deal about that today. This comes about in various descriptions. Darwin talked about the tangled bank. We're concerned about the whole of the system, but how does we relate that to the parts? Is there a balance in nature? All of these have to do with the complexity of these systems. So just like in physics, where we're dealing with complex systems all the time. For example, when you go to boil water or to create pressure to transform a liquid into a gas, or to change a liquid into a solid like ice, that involves the movement of millions of molecules banging into each other. But you don't sit down and make those calculations every time you go to boil water. Physics has developed ways to relate the microscopic to the macroscopic, thermodynamics and statistical mechanics. And we really have a challenge to do the same sorts of things in dealing with environmental problems. And I'll talk a great deal about that. How do you go from individuals to the macroscopic properties of the collective? The fourth obstacle I want to talk about is the present as the enemy of the future. How do we discount the future? How do we manage to give importance to future generations? You may recognize this young man. He's in the audience today, along with his father. How much should we leave to future generations? So this is a great challenge, and I'll talk a little bit about this, but this is a problem of been of terrific interest to me. And the last obstacle I want to talk about is us, people, the most dangerous species, and the challenges faced the commons. This says, give a man a fish, he eats for a day. Teach a man to fish, he eats for a lifetime. Overfish, and soon no one eats. So how do we control our appetites that are bigger than they need to be? But these obstacles give rise to opportunities, I think, and what I'm going to concentrate the rest of my presentation on is what I think some of these opportunities are. So despite the individuality of ecosystems, there are characteristic regularities that exist in the macroscopic patterns, whether you're dealing with forests or freshwater systems or marine systems. There are certain features that we recognize, and those are the features that sustain what we call ecosystem services that are important to the way we utilize these systems, despite the differences in detail. We can't be concerned with maintaining every feature of every system because they change naturally, but there are certain macroscopic features we need to identify, and those should be the focus of research on sustainability. So to get there, that means we have to know how to relate phenomena across scales, which is where most of my work is, from cells to organisms, from organisms to groups of organisms, from those groups of organisms up to ecosystems and the biosphere, and to ask questions like how robust are the properties that we depend upon? How does the robustness at the macroscopic scale depend upon finer scale dynamics on ecological and evolutionary time scales? And are ecosystems at critical points where they're in danger of collapse or sudden change? Are we about to lose the general circulation patterns of the oceans, et cetera? So much of my research and much of the research in theoretical ecology has been directed at trying to understand the macroscopic features, like in this forest system, in terms of the dynamics of individuals, like the trees that make up this system. This is work we did about almost 20 years ago, but based on the work of many other people like my colleagues Steve Piccola, Dan Botkin, and Henk Schugert. Models of this sort are very good at predicting some of the statistical properties of the distributions, but not obviously where every tree is going to be. Indeed, vegetation models that extend these up to the global scale explain global patterns, but not individual species, but going back to that slide I showed earlier of the kinds of vegetation one would see in a particular region. And people have applied models of this sort to other systems. Mick Follows, working with Penny Chisholm and others, has developed a model called Darwin, which makes predictions about where one might find ecotypes, groups of species, diatoms, large eukaryotes, not individual species, again, but these models have been very successful at predicting in testable ways the distribution of organisms on the planet. And we've been working with Mick and his group to try to look at this in an evolutionary perspective. So ecosystems and the biosphere are indeed made up of these individual agents. They're what we call complex adaptive system. This wonderful movie given to me by Claudio Carreri is of starlings in Rome. Well, all except for this hawk that you can see here, which is driving this whole behavior. And so we have largely, if you're a fluid dynamicist, which is where I did my training, you look at this and you say, I have to be able to model that as a fluid. How do these macroscopic patterns emerge when individuals are simply paying attention to local conditions, to their nearest neighbors, for example? Complex adaptive systems are systems like this, heterogeneous collections of individual agents, and could be in the stock market as well, that interact locally and evolve, I don't mean in a genetic sense, but change based on the outcomes of those interactions. And this is a novel way to look at these systems. You saw my slide earlier talking about the management of forests as complex adaptive systems, a new paradigm that seems to be emerging. But not only the ecological systems, but also the socioeconomic systems with which they are linked are complex adaptive systems made up of individual agents. In 2008, working with colleagues Robert May and George Sugihara, and coming from a meeting on systemic risk that was held at the New York Fed, we published a paper in Nature that said, we're just humble ecologists, we don't know much, but it looks like there's a lot of common ground between financial systems and ecosystems, and if we were working on your systems, we'd be worried. We said, who knows, for example, how the present concern over subprime loans will pan out? So this was 6 months before the market collapsed, and then the market collapsed. So as I told people last night, I wish, in addition to writing this paper, I had read it and believed it. But indeed, the market collapsed, and not because of our paper, but I think because of the reasons we identified. The system had become overconnected. So there are great parallels between ecological and economic systems. Many such systems, many such transitions have characteristic early warning signals. Martin Skeffer has published a book, actually in a series I edit, on critical transitions in nature and society, and various groups with which I've been involved, been working together to try to determine what the early warning indicators are that systems may be on the verge of collapse, in the hopes that if you can read those signals, you can step back from it. And I don't have time to talk about this in detail. There are some promising signs, and there's also the danger of overinterpreting some of these signals, but I think it's a very exciting area for study. Scientific consensus on many of the issues that all of us are concerned about is strong. For example, in terms of climate change and the increasing temperature, and yet we haven't done enough to address that. Why? I don't think it's because we don't have the scientific knowledge. Of course, there are aspects of the science that we don't understand, but this is not the primary limitation. The primary limitation is on the side of the social sciences, on the side of the willingness of people and governments to commit to the common good, and to cooperate in finding solutions that benefit everyone. So I think that's where the great challenge is, and that's where I'm going to spend much of the rest of my time today. The central issues are issues of behavior and of culture. My colleague Paul Ehrlich has led the development of something called the Millennium Assessment of Human Behavior, which says this is the key thing in dealing with environmental problems. We have to understand why people make the decisions they make, what the role of collective decision-making is, in the hopes that we can influence these decisions. So these involve issues of equity, both intergenerational and intragenerational. I'll talk about both of those briefly. These involve problems of public goods and common pool resources. Public goods are things like clean air that we all share, and differ from common pool resources only in the notion that with a public good, my use of it doesn't limit your ability to use it. Common pool resources would be things like fisheries. How do we get cooperation in the commons? What's the role of social norms and institutions and agreements? Foot binding was widespread in China among certain classes for centuries, but then, and very robust, but then suddenly disappeared over a very short period of time. How did this social norm change, and what can we learn from how this changed, how attitudes towards gender equality, smoking in public, racial equality changed in this country? There are examples where attitudes have changed. Indeed, in 2008, before the crash, Jeff Sachs, an economist at Columbia, came and lectured at Princeton, and he said the attitudes were changing. People were accepting that climate change was a serious problem, that humans were responsible, and we needed to do something about it. But then the financial crash came, and suddenly these issues were placed on the back burner. There was a dramatic attitudinal change. I'll come back to that in just a moment. We also have to understand how we develop these consensus. So this is what I wanted to indicate to you about attitudes. This is a study that came out of RFF, of which I'm a so-called university fellow. And I don't know if you can see that. Do we need to turn the lights off here, or is this? It's okay. So this is a study carried out in the US, in China, and in Sweden. And the question that was asked is, do you believe that temperature has not increased globally? In China, only 5% of the people thought that that was true. 95% believed that temperatures were increasing. In Sweden, it was 94%, indistinguishable. In the United States, 24% thought they had not changed. So way down, 76% believed that this was a problem. It gets worse. What percentage believe that humans have affected temperature increase? In China, 96% thought humans were responsible. In Sweden, 94%. In the US, only 73%. What accounts for this? Well, obviously, we have to do a better job of informing and understand the culture and how this has happened. And finally, should we prioritize environmental improvements even if we lose jobs? In China, 77% said yes. In Sweden, 62%. In the US, only 40% regarded this as important. So obviously, it's culturally dependent, and understanding why will help us to understand what we have to do about it. One of the issues is equity. We discount. This is a picture my wife took of me not too long ago. You know, I know I shouldn't overeat. We all know we shouldn't overeat, but when it's in front of you and it looks good, you're tempted to eat. So we discount the future. And that's very important. What rate do we use to discount the future? The Stern report on climate change, one of the most influential reports on climate change and what we need to do about it. And the recommendations that came out of the Stern report is that we had to do something about it, but it's very dependent on the discount rate that he chose to use. And there's lots of debate about what the discount rate is. The discount rate means how much you value the future compared to the present. And the higher the discount rate, the less importance you place on the future, and the more you are likely to overconsume now. A lot of debate in the economics community and other communities about, because we shouldn't leave it to economists, of course, about what the discount rate should be. We also discount the interests of others. This is not a true picture yet, but it could be our future. Cell phones on airplanes, can you imagine? When your neighbor, sitting on the train and listening to people talk the whole way is bad enough, and you can sympathize with this gentleman. So we discount the interests of others. So intergenerational equity is only part of the problem. We have to worry also about intragenerational equity. We need to consider issues of fairness. This is a picture taken in Sao Paulo. I didn't take it, but I was just there 2 months ago, where very wealthy and rich areas sit right next to poor areas. Great contrast. This shows you the inequity in the distribution of wealth. This is in the United States. This is the ratio of the wealthiest 1% to the median wealth. Already in 1962, that was 125 to 1. By 2004, it was up to 190, and it's continued to increase ever since. So understanding this is a great puzzle, and I'm not going to argue that everybody should have the same amount, but increasing inequity is a problem of great concern in dealing with a wide range of problems. The difficulty is we live in a global commons. Individual agents act in their own self-interest, and the social costs of our actions are not adequately accounted for. Indeed, even if we're concerned about it, most of us don't believe that our own actions add very much, and to some extent that's going to be true. And so how do you develop a culture where everybody's making only small inputs and could only do small amounts to improve the situation? But yet, if it's like with voting, if nobody went and voted, we'd have problems with elections. So the challenge is, how do we achieve cooperation at the global level. And the problem is free riders like this guy here, who free ride on the benefits, the collective benefits, but don't pay the price. The prototypical problem that people in the economics literature have considered here is the prisoner's dilemma. The prisoner's dilemma says two prisoners who both are suspected of taking part in a particular crime. They're placed in separate rooms. Each one is told there's enough information on them to send them to prison, but if they will give some evidence, their sentences will be reduced unless the other person gives evidence, in which case they both end up worse off. So if they both end up cooperating with the authorities, that is defecting from cooperating with each other, they'll both be worse off. What they ought to do is to get together and cooperate and say, we're not going to give any information. But separated, the temptations are too great. And John Nash won the Nobel Prize demonstrating that the only so-called Nash equilibrium, essentially the only stable solution, is one in which both defect. And yet we know there's cooperation in nature, so how do we get there, and what can we learn from this? For public goods, this is called the tragedy of the commons, an idea introduced 2 centuries ago by William Forster Lloyd. The idea is that we share these grazing grounds, but there's a problem in that nobody's got enough interest in maintaining this. This was rediscovered by Garrett Hardin in the 1950s, who wrote a very influential paper. It's been cited tens of thousands of times in science. And this is Elinor Ostrom, who was a colleague of mine, who actually tested out Hardin's solution, which is mutual coercion, mutually agreed upon. We developed cooperative arrangements that police cooperation, and Lynn Ostrom demonstrated this in a variety of applications, in particular in small fisheries, and won the Nobel Prize for her work. So I'll come back to this theme, but in societies, we develop things like insurance agreements. The Tylers made their fame and fortune in the Farmers Insurance Group. Insurance is a way that we band together to deal with risk and uncertainty, and in a way we create public goods and common pool resources. So I've been working on a number of problems of this sort, of insurance agreements, with Avinash Dixit, a distinguished economist at Princeton, and Dan Rubenstein, a colleague in my department, actually my chairman in ecology. Dan works on herdsmen in East Africa who share grazing grounds. The idea being, if I'm having a bad year in terms of climate, I don't have a place to graze my cattle, I want to send them to, and ask you if you will accept them, and you say, why should I do that? And I say, well, next year the situation may be reversed, you can send yours to me. And so that's the essence of a cooperative insurance arrangement, and we investigate the conditions under which this will work, and if it won't, are there so-called second best solutions that will work in a game theoretic sense. We have lots of examples, and there have been lots of studies shown that individuals will pay a price themselves to punish others who don't follow the rules of the game, if their sense of fairness has been violated. Ernst Fair, aptly named, has done numerous studies, many other people, showing that individuals will pay a price to punish others who don't contribute to the public good. One game that's been much studied by economists and other social scientists is called the Ultimatum Game. I give Maya here $100,000, and which I may do, which she has to share with someone in the back whom she doesn't know, and you, Amber, okay. Well, she knows you, Amber, and she will only play this game once. And what Maya has to do is to offer Amber a share of the $100,000, whatever share she wants to give her. She can offer her half or $1 or whatever, and then Amber has to decide whether to accept. If Amber accepts, everything's fine, but if Amber turns it down, neither one of them gets anything. So the question is, how much should Maya offer? And I play this game in my class, and one student offers the other $30,000 in this situation, and she turned it down. And I said, by turning it down, you're turning down it's going to cost you $30,000. And she said, yeah, but it's going to cost him $70,000. So this is the principle. Most of us would not turn down $30,000, but most of us would probably turn down $3. It's worth it to us to punish that person who has violated a fairness norm. Even though there's no negotiation, we'll never play this game again. So this has been played in various cultures, and there are very different standards about what people offer and what people will accept. But across the cultures, people will pay a price to punish others who have violated some social norm, even though it doesn't make sense within the context of that particular interaction. It's somehow embedded in some broader framework. So these social norms are crucial to understanding how we get cooperation in society. With two former students, Alessandro Tavoni and Maya Schluter, I've been doing work which looks at fisheries withdrawal systems, water withdrawal systems, in which you have a cooperative norm, but individuals who withdraw more than the cooperative norm are punished. They're ostracized. And what we examine is under what conditions those sorts of arrangements are stable. How do you sustain these cooperative norms? How do they emerge? What's the role of pro-sociality in smaller groups, which is concern for other individuals? So these examples, I think, are of specific interest, but more broadly, they're models for how do we address international cooperation. Can we learn from what goes on in nature, cooperation, and the dynamics of collective phenomena like the birds that I showed you before about how people interact? Obviously, people are different, but what can we learn from it? Public goods problems are widespread. This is the sort of commons that I showed you before, and this is a picture that Carol took when we were in South Africa of a termite mound, which is a cooperative phenomenon, which produces a public good. So these are widespread. You heard in the introduction some discussion of nitrogen fixation. Nitrogen fixation is the way that plants, for example, convert nitrogen that can't be used into usable forms, generally through partnerships, for example, with bacteria or mycorrhizae. But nitrogen fixation is costly. You have to produce a nodule. You have to make an investment in it. And if I'm fixing nitrogen and you're right next to me and you're not paying the price of fixing nitrogen, you still gain from the nitrogen in the soil. So it introduces the potential for cheating. So this is a public goods problem, very similar to the ones we face in our societies. Tumors are a breakdown of the commons because the tumor itself is the profligate spread of and growth of some cells, ultimately at the expense of the organism they're part of. So it's a breakdown of, the organism is a public good in a sense. Indeed, this was the cover of Nature last week, which turns the problem around. Tumor cells produce certain compounds, cytokines and things that are crucial to the development of the tumor. So if you could interfere with that level of cooperation, this might be actually a way to deal with cancer. And so working with David Dingley and George Pacheco, I've begun to look at these problems of how do you use this in reverse, perhaps to deal with the problem of cancer. Even bacteria cooperate. When you go to the dentist, it's because of the plaque on your teeth, which is a biofilm of many, many species of bacteria, which send signals to each other and exude extracellular polymers that create a matrix for growth. So all of these are examples of the production of public goods in nature. So what can we learn from nature? These are leafcutter ants engaging in some collective activity where they take the leaves to their common home. This bothered Charles Darwin. It was a puzzle for him. It delayed the publication of The Origin of Species for 20 years as he tried to understand, in particular, in the social insects, why females would give up their own fitness to help their sisters and under what conditions. And this remains an area of great debate. Darwin never really figured it out. J.B.S. Haldane reportedly said that he had the answer. He said, I would give up my life for two brothers. I would jump in the river, is what I think he said, for two brothers or for 8 cousins, making the calculation of the degree of genetic relatedness. W.D. Hamilton, who wrote his thesis on this topic, never really believed Haldane said that, but this is a different story. Hamilton focused especially on the social insects. In the social insects, the bees, the ants, the wasps, the males come from unfertilized eggs. So the system is called haplodiploid. That means that males come from unfertilized eggs, so the females who have the same father share 3/4 of their gene, making cooperation much easier. So genetic relatedness can help, although this has remained a very controversial area. And E.O. Wilson, who was a great supporter of this idea when it first came out, a previous winner of the Tyler Prize, has recently changed his mind. I don't want to enter that debate, but it's clear that close genetic relationship is not essential for cooperation. These oxpeckers on the back of this animal are helping to prune it and obviously gaining something from it. This is a cooperative arrangement. Individuals engage in reciprocal altruism, helping each other. We became interested in the role of leadership in these systems. This is work with Ian Cousin, my former postdoc, now colleague at Princeton. This we published in Nature in 2005. And what we did is we built a model. If I ever say I mean we here, okay. But if I say we, I probably mean Ian did it. And so in this, we have individual fish who have a certain direction. They're moving through the system, and they change their directionality at each point in time in relationship both to their own information and the information of what their neighbors are doing. So it's a trade-off between do I find information myself or do I steal it from my neighbors? It's a fundamental problem. It's related to the essential question of exploration versus exploitation as well. So in the first movie I'll show you, there are 100 fish. Only one of them has any idea where it wants to go. The other 99 are just sort of wandering around. They keep pulling that one back in. So the white dot on the front is the so-called informed individual. This blob goes nowhere. If I raise it up to 5, it moves haltingly here. And in this movie, there are 10 who want to go here, and the group moves rather quickly to it. So animal groups can be led by a very small number of individuals. These are groups of different sizes. And as you can see, by the time I get up to 5 or 10 individuals, the group moves about as fast as it can up to the goal. But not only animal groups, but human societies as well. We're being led by the lemmings off the cliff. We're led by a very small number of individuals who actually are making independent decisions. Think about it in terms of who's making the decisions for you and the degree to which we tend to follow others. What happens if not all the individuals want to go the same way? 5 want to go here, 5 want to go there. The group's either got to make a collective decision or split. So we've done a lot of work studying the conditions under which they will make a consensus decision. And we find that unopinionated individuals are crucial to the development of consensus here. And this is an active area of work for us. So my argument is that the greatest need for us is to understand how individuals make decisions and how collective decisions are made, which means we're going to have to build bridges from science and management to the social sciences in order to understand human decisions, and especially to the roles of leadership and of collective opinion. Ecological systems and socioeconomic systems alike are complex adaptive systems made up of individual agents with emergent properties that feed back. Adam Smith is often cited in the economics literature for talking about the invisible hand, the idea that economies left to their own will reach efficient equilibria. But as we learned in 2008, if we didn't know it before, the invisible hand doesn't protect society. We'll reach some equilibrium, but there's no reason to expect it'll be one we like. In environmental system, these lessons are magnified. People talk about Gaia, that systems will self-organize and reach equilibria. And that's probably true, but it's not it may be an equilibrium in which we are no longer partners. And so we can learn from the environmental systems for economic systems and vice versa. The complex adaptive system perspective, I think, means that in both cases, and we just, Ken Arrow and Paul Ehrlich and I just had a paper that came out a week ago in which we made these points. In both cases, management's going to require a balance between laissez-faire, free market, and regulation. Finding that balance is the trick. We're going to need, for environmental systems, new institutions, and they're going to have to be adaptive. My favorite example is the human immune system, which has evolved in response to the fact that we are predictably going to be faced with pathogens that attack our bodies, but not predictable which pathogens they're going to be. And so we need a system that has early warning signals, that has generalized responses that buy us time, and it has adaptive responses that learn and protect us the next time around. And whether we're dealing with bioterrorism or financial markets or environmental systems, we're going to need adaptive institutions. And how do we build up to deal with problems of climate change? Lynn Ostrom argued we need polycentric approaches, and we've been trying to build on that. I accept her arguments. That means you build local agreements, and these become modules, building blocks, for getting first the US and China, Western Europe, et cetera, building up. Trying to get 200 nations all at once to agree is probably hopeless. Can cooperation be extended to the global level? This is the G19 now. This is the great challenge facing us. Unfortunately, what we learned from natural systems is the emergence of cooperation within groups, of which we have multiple examples, is often for the benefit of conflict with other groups. And getting back to where I began, getting back to Pogo, in the global commons, there is no other. He says it's hard working on all this stuff, and Pogo says, yep, son, we have met the enemy, and he is us. And therefore, understanding how to achieve international cooperation, we're going to have to do like we did in the movie Independence Day. It's at the core of achieving stability and dealing with our common enemy, which is environmental degradation. We have to recognize it's not another culture, it's environmental degradation, so that we can achieve a sustainable future for our children and our grandchildren. Thank you very much.